This is the Grand Union Canal at Tring in Hertfordshire. It's the highest point of the canal before the long and heavily locked stretch down into London, or, heading north, the meandering downward journey towards Milton Keynes. And those locks, essential though they are for lifting and lowering boats over the contours of the land, cause a problem. Every time a canal lock is used, thousands of gallons of water flow downhill. It doesn't matter which way the boat's going, the water always goes downhill. And with canals being entirely man-made and not naturally fed like rivers or streams, you'd think eventually the highest pound would run dry. So why doesn't it? Here's an illustration to show more clearly what I mean. There's a canal pound at the top of the slope, a canal pound below, and a lock between them. Every time the lock is used, water drains from the top pound. Eventually, it would run dry if it wasn't refilled. But from where?
We've got about 70 reservoirs. Those 70 reservoirs were built to feed the canal system with water, and they still do that to this day. That adds up to about 50% of our total water for the canal network. Some canals have got a lot of reservoirs, some canals have got no reservoirs at all. So we blend the reservoir water with other sources of water. So we can take water out of rivers and streams, we can pump water out of the ground, so out of the underground water table. The goal for us is always about levels, maintaining a level for navigation, for boating. We don't want the level to get too high because the water will spill over the weirs and it'll go to waste, or it could cause problems to local neighbours or go on the towpath. If the level's too low, then the boats will hit the bottom. So we're trying to hit that sweet spot, that what we call a normal operating zone of water level. For some canals, that tolerance is quite broad, quite wide. Others, it's quite a narrow little threshold that we have to stick within.
And whilst 200 years ago those levels would have been checked and monitored by a team of lengthsmen, each responsible for a section of canal, nowadays the manual approach is supplemented by technology.
We have guys on the ground 365 days a year that manage the water levels. It's also managed through a system we call SCADA, which can be seen on any device, laptop, and we can monitor the levels that way. That's where we know what we're feeding from each reservoir, we know where the levels are at certain areas, and that's how we know to tweak things.
That's the theory then. But just digging a load of reservoirs doesn't of itself sort the problem. You still need to move the water around, from reservoir to canal, maybe from reservoir to reservoir, and from lower parts of the canal back up again.
There are lots of pumping stations around the network. Obviously, the reservoirs are usually, sometimes they're at a high point and sometimes they're at a low point. If the reservoirs are high, then you can have a gravity feed into the canal system, and so you don't necessarily need a pumping station. When the reservoirs are much lower, or you have a canal that comes up to the summit, you then need to get water pumped out of the reservoir up to the summit to then feed the canal network. And some lock flights, particularly longer ones, have what's called a back pumping system. And so the back pumping system is a localised system, usually all underground, both the pumps and the pipework, and that is sucking water from the bottom of the lock flight up the towpath usually, or maybe across the field, but again in pipes, and discharging it at the top of the lock.
This is the Wendover Arm. It was built in the 1790s, specifically to feed water into the summit pound of the Grand Union Canal. 4 massive reservoirs were also dug. Drawing the water from those reservoirs and into the arm is this, the Tringford pumping station.
The building itself was built in 1817, only took a couple of years, and it was built with the help of Thomas Telford. The building has 3 wells within it, and within each well is a separate pump, and so you can use the pumps to suck water, if you will, from different parts of the reservoirs and discharge it at different times into different places up into the canal. The pumps here can each shift about between 150 and 200 litres per second. That's probably 3 to 4 Olympic swimming pools per day of water that we're taking out of the reservoir and putting up into the canal.
Peer down well number 2, for example, and you can see the water below. That water now comes up the blue pipe attached to the side of the wall. The 2 grey tubes are guides on which the pump can be raised or lowered into place for maintenance, hauled up on this chain. Cunningly, the pump sucks itself into a watertight position once it's lowered down. When the water's pumped up, it first goes into this stilling pool. and from there feeds the Wendover Arm, which is just about visible through the trees. That, as already mentioned, in turn feeds to the Grand Union Canal summit. This glorious old diagram shows a schematic of the station and the 3 wells drawing from each reservoir. And this old map shows where the pumping station lies in relation to the water supplies. Having so many reservoirs makes Tringford rather complex in canal terms.
In principle, it's simple: water out the reservoir into the canal, keep the boats floating. However, at Tringford, we have 4 reservoirs. We have Milesworth, Startops, Tringford and Wilston. And depending on which pump you're running out of which pumping well, you can draw water from different places to different pumps to keep the levels in the reservoirs consistent, or if you've got a problem in one reservoir you can lower it, or if you want more water in the other one you can raise it. So all the pumps originally and all the wells and all the reservoirs were all interchangeable. The modern day approach is 1 pump to 1 well.
Tringford is currently undergoing a huge modernisation project, but has kept some of the old equipment on display for occasional heritage open days. This is a pump from 1912, driven by a 1960s electric motor connected via a drive shaft. The pump would have pushed water up this pipe from the well below to the level of the canal, with filtering of any muck done by meshes like this. When it was built 200 years ago, steam-powered pumps were installed, but they were replaced by diesel-electric units in the 1900s, hence all the lovely old high-power switchgear. Now a touchscreen in a cupboard hints at updates to the system in the last couple of years, which swapped in modern electric motors. And where once directing the flow of water used to be done manually by turning valves and opening sluices, now it's electronically controlled too. Modernising so much old infrastructure like this across more than 2,000 miles of canals and rivers is, to say the least, a challenge for the Canal and River Trust.
With an ageing network that is over 200 years old in places, it is a really tough sort of process to decide what do we spend money on and what we're not going to spend money on from one year to the next. Sometimes we get unplanned failures. Sometimes an asset that we think was sort of in not great condition but not awful condition sometimes fails, and that could usually be to do with an external event. Something happens that we couldn't predict or plan for, like a big storm event, a big flood event that washes away the edge of a canal bank or causes damage to a lock flight, and then we have to do sort of reactive work to repair that.
And flood prevention is a critical aspect of the system, but the engineers who built the canal network in the 17 and 1800s were astute enough to have this in mind. They built in mechanisms to let water drain along the system if the levels rise too high.
Some lock flights have what we call a bywash, which is a channel that goes around the side of the lock, and that allows the water to bypass it. Some locks, as per the Aylesbury Arm, which is quite local to here, that allows water to weir over the gates, so there isn't a side channel, it weirs over the gates. Grand Union Canal maybe, Hatton, which is obviously a well-known flight, that has letterbox weirs. So as well as having the channels on the side, it has a letterbox weir, which is like a slit behind the top gate, and the water can flow over that, through that letterbox into the lock chamber, fill the lock chamber up, if the bottom gates are sealed obviously, and then wears out the bottom letterbox and then carries on its flow.
There's just as much of a challenge for too much water, and probably more of a challenge because of the time periods in which it can happen. So quickly a flood event can come from almost nowhere. We get rainfall predictions and weather forecasts which help us, but we don't exactly know where the rain is going to land and exactly what impact it might have. Some of our canals sit in steep-sided valleys. The Rochdale Canal sits in the valley of the River Calder, and in 2015, on Boxing Day, we suffered, along with the communities in the area, some very significant flooding damage. I think it was well over £10 million of damage to our canals, where the river and the canal literally became one. There was so much water around, coming off the steep-sided valleys and off the hillsides. There was nowhere for the water to go quick enough. And what we're seeing with climate change and more extremes of flooding is that they're happening more often, they're more intense, they're hard to predict, they can happen in the summer, not just the winter, and for us it's a real challenge almost keeping pace with that changing climate, those intense rainfall events, that when they hit, the effect can be quite dramatic. Making our canals completely resilient to every possibility of climate change is probably unaffordable. But one of the big challenges for us is choosing, well, where do we make our system more resilient? Where do we invest to make the weirs longer, to make the sluices bigger, or maybe to automate them, perhaps bringing in more monitoring so we can actually react more quickly when the levels start to rise.
And that brings us here, to Todd Brook in Derbyshire. This little stream trickles down to feed a huge reservoir that sits right on the edge of the town of Whaley Bridge. The water, more than 1.3 billion litres of it, is a crucial supply to the Macclesfield and Peak Forest canals. But for the last 2 years, the stream's path to the reservoir has been blocked off, with the feed diverted around the edge and away into a river. The reservoir itself lies practically empty. It's been kept like that because of a near disaster in 2019. On the evening of July 31st, a deluge of rain left the reservoir full, quite literally to bursting. The pressure behind this concrete spillway, which is designed to direct overflows safely away, became too much, and the concrete started to bulge and crack. If it had burst, all the water, all 1.3 billion litres, could have cascaded over Whaley Bridge. The town had to be evacuated. Police, fire and the military were brought in, using RAF Chinook helicopters to drop huge bags of rubble onto the site to shore it up. Because of that, and because the reservoir was quickly emptied with huge pumps into a nearby river, the town was saved. Since then, Todd Brook Reservoir's been kept deliberately low, with those pumps and pipes pushing any excess water straight out to the river. What nobody had realised, despite regular surveys since it was built in the 1970s, was that the spillway suffered from a fundamental design flaw, essentially that it was leaking, letting water through the sides of the reservoir, weakening the concrete. Now, Todd Brook won't be allowed to fill again until an entirely new spillway system has been built, with these illustrations of the proposed design being produced by the Canal and River Trust.
The auxiliary spillway itself will be decommissioned as part of the work we'll be doing. And there will be an entirely new spillway structure which will fulfil the purpose of both the primary and the auxiliary spillway combined, and that will safely cope with the overflow capacity needed from the reservoir. You can see behind me is where the new weir will be located. That's where the reservoir will overflow into a tumble bay. That then drops down a spillway channel into a stilling basin at the base, and it'll run through a low flow channel in Memorial Park to the River Goyt.
The storm that prompted the near disaster was said to be a 1-in-100-year event, but our weather does seem to be getting crazier all the time. Given that no one realised there was a design flaw in the spillway, residents might be forgiven for querying whether this could ever happen again.
Once there's been an incident, nobody wants lightning to strike twice. So the effort that we're putting into the modelling and the simulation and the engineering design for Todd Brook is absolutely world class. You know, the amount of money and time we're spending to get that design right, to absolutely ensure that every risk is planned for. We've got computer simulation modelling. We've got much better understanding than we had in the 1960s and 70s of the way that dams evolve and the way that they might fail. There is no chance that the trust or the government would let us rebuild that reservoir in a way that was in any way compromising safety. And in fact, we're actually looking at all of the usual risks, plus things like earthquake risk. So you wouldn't think that the Peak District was particularly prone to earthquakes, but we're looking at extreme events that have got a very low likelihood of happening. But we're looking at all of those because the dam has to stay intact and face up to all kinds of things. Floods, earthquakes, the whole lot.
For the people who manage the canals every day, and for boaters, the loss of a reservoir has a big impact, as it means that other sources of water have to be found to top up the canals.
It's been a huge disruption for us losing Todd Brook. It's put the emphasis on the 3 remaining reservoirs on the patch to maintain those water levels. You can see the pumps running behind us, which is pumping water from Coombs Reservoir, bypassing the feeder, using the River Goyt, and then feeding straight into the canal. It means we've got to feed a little bit more from the Macclesfield side as well, which is putting the emphasis on Bosley and Sutton reservoirs. Sutton's only a very small reservoir. Bosley's quite a large one, so we can feed a little bit more from there. But it has caused us to, unfortunately, the necessity to put in some restrictions on both lock flights at Marple and Bosley to manage those waters, to give us enough to last us through the summer season.
Across the canal network, water loss is not uncommon. It can be caused by vandalism, maintenance issues, leakage, or sometimes boaters leaving the sluices open by accident or ignorance. When water resources are scarce, keeping boats floating is a group effort.
We have a team of absolutely amazing lock keepers on both the Marple and the Bosley flights, and they help us manage the boats up and down the flights, and they'll manage it in a way that we reduce the amount of water that we use. By closing the locks at 4 p.m. and not opening them again till 8 a.m. the next morning, that means that it's got further time to recharge the levels overnight.
They might seem like simple water-filled ditches, but the British canals are really quite a complex network of engineering, all the more impressive for having been dug by hand over 200 years ago. And their relevance today is becoming all the more critical, not just for leisure, but as a part of the whole country's infrastructure.
We're really aspiring to be much better water managers. I think we can be more efficient in the way we use water. I think a lot of the ways we use water are quite basic at times. We have got a lot of investment. We have put a lot of money into instrumentation, computer modelling and simulation, but there's still a long way to go to catch up with the water companies. And if we want to be part of the solution in terms of UK PLC having enough water, whether that's for boating, whether that's for agriculture, whether it's for the environment, or public water supply and drinking water, then we need to sort of up our game considerably. And I think government recognise that. They see there's an opportunity with our network. Our network cuts across catchments and water company boundaries. We're one of the few organisations that has that ownership of a ready-made transfer route to be able to move water around. So we need to continually invest and improve in what we do. But I think we've come on a long way in the last 20 years since I've been working for the Trust. And I think the next 20 years of my career, hopefully, will take us even further.